Hello, everyone. My name is Elisabeth Pangratz, and I'm happy to present you our paper with the topic Towards an Implicit Metric of Sensory Motor Accuracy, Brain Responses to Auditory Prediction Errors in Pianists. So, to give you a short introduction how auditory prediction is generated during music performance, you can have a look at this picture on the right side. So when someone plays an instrument, auditory and motor systems in the brain work closely together. So someone has to perform a movement generated by a motor command and expects a specific auditory feedback. So the sound that he picks up through his ears. Then this auditory feedback is also internally evaluated in the brain and also is used for self-monitoring and also influences the next movements. So this kind of works as a motor auditory feedback loop and allows for generating these auditory predictions. So what we were addressing in our investigations were how does the brain actually react to when these type of auditory predictions are violated? So specifically, we were asking, how does the brain react to auditory expectancy violations during piano performance compared to piano perception? So when they only listen to the piano. So in piano performance, as I said, this expectancy is influenced by the motor actions, but also by musical rules, because they also simultaneously listen to the musical piece, and expectancy can be generated by the musical context. Now, in piano perception, so when they listen to the piano, expectancy is only created based on musical rules from the context. Then secondly, we were asking how this brain response is modulated by the type of expectancy violation. And here we investigated two distinct acoustic features. First of those was pitch, which corresponds to harmonic expectancy. And the second is loudness, which corresponds to the regularity of sound. And specifically, we realized 4 types of manipulations to investigate this, and those were harmonic and dissonant pitch manipulations. Where dissonant pitch manipulations sound rather like out of key and disharmonic, and small increases in loudness compared to large increases in loudness. So such brain responses to auditory expectancy violations can be picked up via electroencephalography. So here, 64 electrodes are put on the scalp of the test subjects, as you can see here on the picture of the right, and they pick up the electricity from the scalp. And the advantage of this type of measuring brain activity is that you can do it with quite high temporal resolution. So in our case, 250 hertz for every 4 milliseconds. And then we investigated the EEG at specific time points, in our case, at the tone onsets. So this is then called event-related potentials. So we conducted our experiment with 7 pianists that were all very well experienced and had on average 20.4 years of piano experience. Here on the right side, you can see one of our test subjects and the setup that we've used. So we used 64 electrodes EEG cap, as I already mentioned. And for the setup, we used a MIDI keyboard where the test subjects played on, and this MIDI keyboard sent MIDI messages to the computer. And here, occasionally, those messages were manipulated by a Python script to realize those manipulations before they were sent to Ableton for sound output, which then the test participants heard through their headphones. For this, we've used predefined piano sequences in different tonalities that were all really simple and structurally similar, and all consisted of chords, so 3 tones played at the same time. And here we manipulated occasionally, in a range of every 10th to 20th chord, a single tone to change the pitch or the loudness. So to illustrate you how this worked, I want to show you a little video of the experiment. So now when you listen closely, you might hear these manipulations. After 5 seconds, you will hear a small loudness manipulation, and after around 25 seconds, a dissonant pitch manipulation. You might hear a dissonant pitch in 1 second. There it was. So this was one of our test subjects in the performance condition, and the perception condition was performed analogously, where they just listened to the sequences. So let's proceed with our findings. Here you can see different ways for each manipulation type for the FCZ electrode. So here you can see the pitch manipulations in the orange-like colors and loudness manipulations shown in the blue colors. So let's look at the different components. We looked at the negative deflection, which had different peak latencies for pitch and loudness manipulations. So here we can see that the latencies for the negative going peaks were shorter for loudness manipulations compared to pitch manipulations, which was also the case for the following positive component. So we see that there is a faster brain response happening here for loudness manipulations. Now, if we compare the performance with the perception condition, we see generally larger amplitudes, showing that the brain reacts stronger here to these violations. And also we can see that the largest expectancy violation, so the largest deflection in the ERP, was shown for large loudness manipulations in the performance condition. So to summarize, we saw that the performance compared to the perception condition showed larger deflections, showing that the intention and the action to produce a sound creates a stronger expectancy and thereby a stronger expectancy violation compared to when they just listen to it. Now, we saw that for the different types of manipulations, we saw distinct features and distinct waveforms. So the loudness compared to the pitch manipulations showed a shorter latency. And so we can conclude that the different manipulations of sound are processed in a different way in the brain. So now we think of how we can make use of these findings. So in the future, it would be interesting to investigate all components of sound. So not only pitch and loudness, but also manipulations of timing or timbre. And then it's interesting to compare brain responses of musicians of different skill levels. So in our study, we had a homogeneous group of only expert pianists, but in the future, it's interesting to see how this behaves for different skill levels and to see if there is a correlation. So with this, we try to contribute to future neuroadaptive music interfaces. So here, one can make use of event-related potentials as a time domain EEG feature with a very small computational overhead, which then allows for real-time adaptation. And we envision to extract some information of the user out from these EEG features, like their weaks and strengths, and get some measures for the sensory motor accuracy and the musical skills. Now then this can be used in intelligent music interfaces to adaptively display educational content, like personal training and exercises. So with this research, we hope to contribute one step further towards neuroadaptive intelligent music interfaces using time domain EEG features. Thank you very much for your attention. Feel free to ask questions if there are any.